Good afternoon to all of you. Is my voice audible? Can you hear
Yes,
me?
sir. Yes, sir. Yes, sir.
So, shall we start the class or is anybody more joining? Shweta has joined it. Okay.
Sir,
Yeah, good. Good afternoon, good evening. So, shall we start the class? Do you remember that where we have reached actually?
Sir, I was
I
absent
hope.
for the last. I was absent for the last 5 classes, so I don't know.
Yeah, so actually we had to study today quantum numbers, right? Isn't it? Have we studied the quantum numbers? Okay. So let me share the screen here. So today topic, it will be very important because we will study these quantum numbers and question is always asked from these quantum numbers. So I hope that this screen is visible to all of you. Is this screen visible?
yes, sir.
Yes, sir.
Okay. So our today's topic is quantum numbers. So actually I have told you that when we actually solve the Schrodinger's wave equation, we get the three numbers, three constants, which are actually known as quantum numbers. But actually we are having, in total we are having four quantum numbers. So what are actually these, how to define these? So you will remember that these are simply set of four numbers. Okay, I will write it here that these are set of four numbers. So that means we are having quantum numbers are in total four. So these are set of four numbers, and which give complete information about an electron. So which gives complete information, which gives complete information of an electron in an atom. So that means what is the energy of an electron, what will be the size of the orbital in which this electron is present, what will be the orientation of the electron, what will be the spin of the electron. Each and every information is actually hidden in these four quantum numbers. So these quantum numbers, they are simply set of four numbers which gives complete information of an electron in an atom. So the first three quantum numbers, they are actually obtained from the solution of Schrodinger wave equation. So okay, I will write it here that the first quantum number is the principal quantum number, principal quantum number, and the second quantum number is known as azimuthal quantum number, azimuthal quantum number, right? And the third one quantum number, that is actually known as magnetic quantum number. So these three quantum numbers, they are actually obtained from the solution of Schrodinger wave equation. When we solve Schrodinger's wave equation, we get these three quantum numbers. But the fourth quantum number is also there, that is actually not obtained from the solution of Schrodinger wave equation, that was separately given by another scientist that is known as Gauss Smith. We will see it in detail. So that is actually known as spin quantum number, spin quantum number. So let us discuss one by one. So let's first see the first quantum number, that is the principal quantum number. So this principal quantum number, it was actually given by Bohr, Neil Bohr. This quantum number, it was given by Neil Bohr. What actually Neil Bohr told, he told that this principal quantum number, it is actually represented by small n. So it is represented by small n. You have to remember that this principal quantum number, it is represented by small n. And what information it gives? It gives information about shells, that is the man energy levels. Okay, I will write it here that it gives information about shells or man energy levels. So it gives information about shells. what we called as man energy levels, right? Shells are also known as energy levels. Actually, in these energy levels, we are having the electrons. Actually, these energy levels, that is the shells, they actually have the subshells, and then they have the orbitals, and in which actually the electrons are present. So it gives information about shells are what we call as man energy levels. Now, this quantum number, that is the principal quantum number, what is the value of n? That is very important. N value, it can be 1, 2, 3, 4, anything. So that is your any positive integer. So that is 1, 2, 3, 4, etc. And we have already discussed this in the Bohr's model also, that if n value is 1, that is actually what? That is your first shell. That is actually known as K shell, right? And similarly, if n value is 2, so that means it's your second shell, that's L. And similarly, if n value is 3, that is your M. And similarly, if n value is 4, so that's your N shell. And similarly, if next n value is 5, so that's your O shell. Then in the alphabetical order, that is O, P, Q, R, etc. So this is the first quantum number, that is a principal quantum number, which gives the information about shells, or what we call as man energy levels. So we are having different shells in case of an atom. And if n value, that is the principal quantum number value, if it is 1, so this is your first shell, that's K shell. If n value is 2, so that's your L shell. If n value is 3, that's your M shell. And similarly, if n value is 4, so that's your N shell, and so on. So have you got it? Shall I move to the next page? Have you noted down this?
Yes, sir.
Okay. So this first quantum number, that is the principal quantum number, it gives information about shells, right? Now you have to remember here the size of these shells. So can you tell me which will have bigger size of shells, or the energy levels? So first of all, we are having K, its size is very small, and then it's your L, and then it's your M, right? N, and then it will be O. So that means as we move away from the nucleus, the size of shell, it increases, the size of the energy level, it increases, right? And similarly, if I just talk of order of energy, so can you tell me which electron will have higher energy? So which will have higher energy and which will have smaller energy? So first we are having K.
K will have
K,
lesser energy.
exactly, it has less energy, then it will be definitely L, M. So that means as we move away from the nucleus, energy increases, right? So definitely O will have more energy than that of N, and this will be the order. So that means order of size and the order of energy, it will be both same. The order of both will be same, right? So this is your first quantum number, that is called the principal quantum number. It gives the information about shells. Now what it explains, so it actually explains the man lines of spectra, what we have actually observed in the hydrogen spectrum. So I will write it here, that it explains man lines of spectra, So that means the man lines which we actually see in the spectra of hydrogen, they are actually due to these shells, due to these man energy levels. So it explains man lines of spectra. This is very important. Now let's move to the second quantum number, that is actually known as azimuthal quantum number. Azimuthal quantum number. So azimuthal quantum number, it is also known as angular momentum quantum number. It's also known as angular momentum quantum number. And this angular momentum quantum number, it's also known as subsidiary quantum number. So you have to remember all these three names. It's also known as subsidiary quantum number. Now tell me that this quantum number, it is represented by small l. So the principal quantum number, that was represented by small n. Azimuthal quantum number, it is represented by small l. Now what is the value of l here, and who gave this quantum number? So this quantum number, it was given by Sommerfeld. It was given by Sommerfeld. So the first quantum number was given by Niels Bohr, And this azimuthal quantum number, it was given by Sommerfeld. And this quantum number, it gives information about subshells, or what we call as sub-energy levels. You will remember that it gives information about subshells, or what we call these subshells as sub-energy levels. So that means within the shells, within the main energy levels, there are also subshells. It is just like if you are having any building, if you are having any complex, first that complex whole, that building, that house, that home acts as a shell. Then we are having different floors. We are having the ground floor, first floor, second floor, third floor. They are just your subshells. And in the subshells, there are orbitals. They are actually the rooms in which the persons live. Similarly, orbitals are the places, the site where the electron actually resides. So you have to remember that this second azimuthal quantum number, angular momentum quantum number, it is represented by small l, and it gives information about subshells or sub-energy levels, and it was given by Sommerfeld. Now, what it explains? So you have to remember that it explains the fine lines of spectra. So that means sometimes in the spectra, we also see some small lines, some sharp lines, small, which are not the main lines. They are actually the fine lines of spectra. So you will remember here that it explains fine lines of spectra. Fine lines of spectra. It explains the fine lines of spectra, right? So how to calculate the value of L here? This is very important. L value is calculated by the formula that is 0 to n minus 1. 0 to n minus 1. So this will be very important. And you have to note down this and you have to apply this. This is very important. So how to calculate the number of subshells? That is given by this formula, that is L is equal to, that is the azimuthal quantum number. It is always equal to 0 to n minus 1. So 0 to n minus 1. What is n? N is the principal quantum number. And I have told you what is the value of n. N value can be either 1, it can be 2, it can be 3. We have discussed this in the first quantum number, that is the principal quantum number. So let's try to calculate the number of subshells, or what we called as sub-energy levels, in the first shell. So shall I move to the next page? Have you noted down this?
Yes, sir.
Okay. So first, let's see the key shell. That is your first shell. So can you tell me what is the value of n for key shell? It is 1, right? Therefore, can you tell me what will be the value of L, that is the azimuthal quantum number? L means 0 to n minus 1, right? 0 to n minus 1. So now here it is 0 to n is here what? N is here 1. So 1 minus 1, what is that?
0.
1 minus, yeah, that is 0. So 0 to 0, what is that? There isn't any number between 0 and 0. That is actually 0. So 0 doesn't here mean nothing. 0 means there is one subshell. This is very important. 0 means one subshell. 0 means here one subshell. Got it? So what is the name of this subshell? Name of this subshell, it is your 1s. So this subshell is actually known as S subshell. One subshell known as S subshell, right? Known as S subshell. So it will be known as 1s, correct? So there is one subshell in this K shell. So that is actually known as S subshell. So that is here actually known as 1s. Now, can you then tell me how many subshells will be in the second shell? That is your L shell. So in L shell, what is the n value? N value is 2. So when n value is 2, so that means therefore L value will be 0 to n minus 1, right? So that is what? that is 0 to n is 2, 2 minus 1, so that is 1. So that is 0 to 1. So 0 to 1 means only two values are possible here. So that is 0 and 1. So that means there are two subshells, right? There are two subshells. There are two subshells. So these two subshells, they are known as, one is known as S subshell, another is known as P subshell. So what will be the name? Name will be given like this, that is 2S subshell and similarly 2P subshell. So these are two subshells which are present in this L shell. Got it? Is it clear?
Yes, sir.
Yeah, so we have learned that in case of first shell, that's your K shell, there is only one subshell, that is 1S. And in case of L shell, there are two subshells, that is 2S and 2P. Then let's move to the M shell. Shall I move to the next page? Have you noted down this?
Yes, sir.
Okay, so let me write M shell, that is the third shell. So what is the N value for this M shell? N value is 3. So that means therefore L value will be 0 to N minus 1. So that is 0 to 3 minus 1. So that is 0 to 2. 0 to 2 means what? It means 0, 1 and 2, right? So that means there are three subshells. In this shell, there are three subshells. So what will be the name of these subshells? So name will be 3S, similarly 3P, and then similarly it will be 3D. 3P and then it will be 3D. Got it? Three S, 3P, and 3D. These are the three subshells which are present in this M shell. So can you then tell me how many subshells will be there in this next, that is your N shell? Can you tell me in case of N shell?
4.
Exactly. There will be 4 subshells. So what will be the name?
4S, 4P, 4D, and
Exactly. 4S, 4P, 4D, and 4F. So can you now tell me where from these terms have actually come? You will remember that this S, P, D, and F, they have actually come from spectroscopy. These are the spectroscopic terms. So they have come from spectroscopy. And what they actually mean, you will remember that S stands for sharp. And similarly, P stands for principal. And D stands for diffuse. And F stands for fundamental. Right? F stands for fundamental. So these are the number of subshells which are present in any particular shell. You will calculate it with the help of L value, that is the azimuthal quantum number, whose value is calculated by the formula that is 0 to N minus 1. Got it? Have you noted down this? Shall I move to the next page?
So 1 minute, sir.
Okay, sure.
Yes, sir, you can continue.
Okay, sure. So next, you will here remember that is that this azimuthal quantum number, it is also known as angular momentum quantum number. Why? Because with the help of this quantum number, we can also calculate angular momentum. That is actually known as orbital angular momentum. So orbital angular momentum, how it is calculated? So you will remember that this orbital angular momentum, it is calculated by the formula that is square root of under root of L into L plus 1 into h upon 2 pi into h upon 2 pi. So I hope that now you can easily calculate the angular momentum of an electron in any subshell. So can you tell me, for example, if I will write that calculate angular momentum of an electron in S subshell. In S subshell. So can you calculate? So for S, you have to remember that L value will be 0, right? For S, L value is 0. Similarly, for P, L value is 1. Similarly, for D, what will be the L value? 2. And for F, L value will be 3. Where we have got this? We have actually got it from these. For example, here you can see that when L value is, when we are having one S, only S subshell. So what is the L value? L value is 0. So that means actually this L value is 0. It is for S. Then we are here having 2S, 2P. So we are having two values. L is here 0 and L is here 1. But 0 is particularly for this 2S, and that means 1 is for this one, that is the P. 1 is for this P. So that is why you have to remember here that for S, L value will be 0. This is very important because this table we will use ahead everywhere. You have to remember this. So what you have to remember that for S, L value will be 0. For P, L value is 1. For D, L value is 2. For F, L value is 3. Now, can you calculate the angular momentum for an electron in S subshell? So how I will calculate the angular momentum? So that is simply square root of L. L is here for S, L value is 0. So 0 into 0 plus 1, right? And then I will write into h upon 2 pi. So what it will become now? 0 plus 1, so that is 1. 1 into 0, that is 0. Square root of 0, that is 0. So everything it will become whole as 0. So that means you have to remember that the angular momentum for an electron in S subshell, it will be 0. This object is asked most of the times, so you have to remember this, that the angular momentum of an electron, it is 0 when it is in the S subshell. Got it?
Yes, sir.
So can you tell me what will be the angular momentum for an electron for P subshell? So for an electron in P subshell, can you calculate the angular momentum? So for P subshell, L value is 1, right? For P, L value is 1. So how I will write? I will write it that it is square root of 1 into 1 plus 1 into h upon 2 pi, right? H upon 2 pi. So that means it will be now 1 plus 1, that is 2. 2 into 1, that's 2. So that is square root of 2 and then h upon 2 pi. So this will be the angular momentum of an electron which is present in P subshell. So I hope that now you can also calculate the angular momentum in D subshell. Can you? For example, if I will write here that you have to tell angular momentum of an electron in D subshell. So can you calculate? So for D, what is the L value? You have to remember this. For D, L value is 2. So that means angular momentum, it will be square root of under root of 2 into 2 plus 1, right? 2 into 2 plus 1, and then it is h upon 2 pi. So that means 2 plus 1, that is 3. 3 2s are 6. So it's under root of 6. Then it is h upon 2 pi, right? So this is how to calculate the angular momentum with this quantum number. So that is why this quantum number is also known as angular momentum quantum number. Got it? So have you noted down this? Shall I move to the next page?
Yes, sir.
Yes, sir.
Okay. So this was your second quantum number, that's known as azimuthal quantum number. Now, if I just talk of size, order of size and order of energy. So can you tell me what will be the order of size and the order of energy for these subshells? So which will have bigger size? Will it be S, P, D, or F? So
F.
S will have smaller size. P has bigger size, right? Then D and then F. F has bigger size. And then Similarly, order of energy. S has smaller energy, right? Then P, then D, and then F. Similarly, if you have to just to tell me the order of size of different s orbitals, for example, if I will write like this, that is, if I'm having, let's say, 1s, 2s, 3s, what will be the order of size? If I'm having 1s, 2s, 3s, so that 1s means it is the s subshell of first shell, 2s means it is the subshell of second shell, 3s means it is the subshell of third shell, right? So can you tell me the order of size? So order of size will be like this. That is 1s, it will have smaller size. 2s will have bigger size. 3s has very big size, and 4s will be having very big size. Got it? Extra. Then let's move to the next quantum number. So that is your magnitude quantum number, right? So this magnitude quantum number, it was given by Landy. And this quantum number, it is represented by small m. And can you tell me this quantum number, it gives information about what? It gives information about orbitals, right? It gives information about orbitals. Clear? So now what it actually explains, so you will remember that it explains the Stark and the Zeeman effect, which we have actually studied in the limitations of Bohr's model. So it explains Stark and Zeeman effect. Stark and Zeeman effect. It explains Stark and Zeeman effect. And I have already told you that what is actually Stark and Zeeman effect. So that is actually the splitting of spectral lines in presence of electric and magnetic field, right? So how to calculate the m value? So this magnetic quantum number, it is calculated by the formula that is minus L through 0 to plus L. Minus L through 0 . Is my voice audible? Can you hear me?
Yes, sir.
Okay. So I hope that you can now calculate the number of orbitals. So with this quantum number, you can calculate the number of orbitals, that is minus L through 0 to plus L. So this magnetic quantum number, it gives information about orbitals. That is the orientation of an electron. So we can say that this quantum number, it gives orientation of an electron. I will write it here that it gives orientation of an electron. That is the direction in which axis this electron will be present. Will it be on the x-axis, y, or the z-axis? So it gives orientation of an electron. So shall I move to the next page? Have you noted down this?
Yes, sir.
Okay. So let's see the number of orbitals in case of different subshells. For example, if I will just first talk of S subshell. So in case of S subshell, what is the L value? L value is 0, right? We have noted down this. L value is 0 for S. Therefore, what will be the M value? M value will also be 0, because what is the formula? Formula is minus L through 0 to plus L. But when L value is 0, so therefore M value will also be 0. So what does this 0 mean? 0 doesn't mean nothing. 0 means there is one value. So that means there is one orbital. And what is that orbital known as? That orbital is known as s orbital. So that means you will remember that orbitals have same name as that of subshells. So it is known as s orbital. It is known as s orbital. So then we are having next is our p subshell, right? We're having p subshell. So can you tell me how many orbitals will be there in p subshell? How to calculate? We know that L value is 1 for p subshell. Therefore, what will be the M value? M value will be minus L through 0 to plus L. And what is here? L value? L value is 1. So that means minus 1. And then we are having 0. And then we are having the plus 1. Correct? So that means we are having the three values, minus 1, 0, and plus 1. So that means there are three orbitals. There are three orbitals. So what is the name of these orbitals here? Orbital name is px, and then py, and then pz. So there are three orbitals in case of p subshell, px, similarly py, and then we are having the pz. Now here you have to note down, this is very important, that for pz, so I will write it here, that for pz, m value is taken as 0. M value is taken as 0. For pz, m value is taken as 0. And then we are left with px and py. So they can have any value. They can have either plus 1 or they can have minus 1. But for pz, this is very important, that for pz, it is fixed that for pz, m value is taken as 0. Because we are having here the three values. One is minus 1, 0, and plus 1. But this 0 is particularly for pz. You have to remember this. This is very important. So then can you tell me how many orbitals will be there in case of d subshell? So in case of d subshell, what is the L value? Yeah, L value is 2. So therefore orbitals will be 5. That means M value will be minus 2 through 0 and then to plus 2. So when it is minus 2, so then definitely it will be plus minus 1, then 0, then plus 1, and then plus 2. So that means we are having total we are having 5 orbitals. Total we are having 5 orbitals. So these orbitals are known as d orbitals, but they have actually the name. So I will write it here. One is known as dxy, another is known as dyz, another is known as dzx. Similarly, another is known as dx square dash y square, another is known as dz square. So these are 5 d orbitals, and here you have to note down that for dz square, m value will be 0. For dz square, m value is taken as 0. So just as we have noted that for pz, m value is taken as 0, similarly for dz square, m value is also taken as 0. So this will be important here. So I hope that you have noted down this. Have you noted down this? Shall I move to the next page? So shall I move to the next page?
Yes, sir.
Okay. So this is the number of orbitals. So similarly for F subshell, you can also calculate for F subshell how many orbitals will be there. So can you calculate? So L value is 3. Therefore, what will be the M value? M value will be minus 3, then through 0, and then through plus 3. So when we are having minus 3, definitely then it will be minus 2, then minus 1, and then it will be 0, then plus 1, then plus 2, and then it will be plus 3. So that means there are total 7 F orbitals. So I'll write it here that there are 7 F orbitals. So F orbitals are 7. And if you can remember, I will just write the name of these. So one is known as Fx cube, another is known as Fy cube, Fz cube, and then next is Fx, Y, and Z. Then we are having Fx, Y square dash Z square. Then we are having Fy, Z square dash X square. Then we are having Fz X square dash Y square. So these are our 7 F orbitals. So if I just tell you that on this 0 value, here you can see this 0 value. So 0 will be for what? For which f orbital? So can you tell me, anybody? For fz cube,
F.
for f, exactly, for fz cube, m value is taken as 0. So this is sign convention, you have to remember this. So this is that with the help of this quantum number, that is the magnetic quantum number, we can tell the number of orbitals in any subshell. For example, in case of s subshell, there is only one orbital, s orbital. But in case of p subshell, there are three orbitals, px, py, pz. Similarly, in case of we are having d subshell, we are having 5d orbitals, that is dxy, dyz, dzx, dx square dash y square dz square. And in case of f subshell, we are having 7 f orbitals, that's fx cube, fy cube, fz cube, fxyz, and similarly fx y square dash z square, and then fy z square dash x square, and similarly fz x square dash y square. So this is your magnetic quantum number that is represented by small m. So then let's move towards the last quantum number that is known as spin quantum number. So have you noted down this? Shall I move to the next page?
Yes, sir.
Okay. So next and the last quantum number, that is our spin quantum number, fourth one. So spin quantum number, it is actually not obtained from the solution of Schrodinger wave equation. It is actually given separately by, this represented by small m, and it was given by Gauss-Smith and Uhlenbeck. So this quantum number, it actually gives the information about spin of an electron. So I will write it here, that it gives information about, spin of an electron. Spin of an electron. So what is spin motion actually? See, whenever we have any electron, it actually, one is the orbital motion, that is it revolves in this orbital. Let's say this is the s orbital, because we know that s orbitals are spherical, right? So let's say this is s orbital. So electron is revolving in this s orbital. So this is known as orbital motion. This is known as orbital motion. But along with that, electron not only revolves in the orbital, it not only moves in the orbital, but it also rotates on its own axis. So that is actually known as spin motion. So that means you have to remember that this electron, it not only rotates in this orbital, but it also spins. So that is known as spin motion. So when it actually rotates on its own axis, it is known as spin motion. It is known as spin motion. So spin motion is shown by the electron. Now spin can be of two types. That means either electron can revolve in the clockwise direction, or it can also revolve in the anti-clockwise direction. So spin are of two types. You will write here that spin are of two types. So one is known as clockwise spin, another is known as anti-clockwise spin. So one is your clockwise spin. It's also known as upspin, and its value is always shown as +1/2 upspin. And similarly, another is our anti-clockwise spin. Anti-clockwise spin. So this is also known as downspin. Downspin. And this is represented by -half. So spin can have only two values. Either spin quantum number can have +half value, that is the clockwise spin, upspin. And similarly, this spin quantum number can have value -half, that is downspin. So that means either electron can just, for example, let's say this is the electron, and it can rotate in this clockwise direction. And similarly, it can also move in the anti-clockwise direction. So it has only two possibilities of spin. So one is that it can spin in the clockwise direction. Another is that it can spin in the anti-clockwise direction. That means spin quantum number, it has only two possible values. One is the plus half, another is the minus half. So have you noted down this? Shall I move to the next page?
Yes, sir.
Okay, so this was the last quantum number, but this last quantum number, it also gives the spin angular momentum. So we can also calculate spin angular momentum of an electron. So angular momentum, it is of two types. One is the orbital angular momentum, which we have already studied in the second quantum number. Another is spin angular momentum. Spin angular momentum, it is calculated by the formula that is square root of under root of s into s plus 1 into h upon 2 pi, h upon 2 pi. So s can have only two values. I have told you that. Okay, let's say, for example, if s value is 1 by 2, that's plus half. So therefore, what I can write, what will be the angular momentum, spin angular momentum? Spin angular momentum will be under root of square root of s is 1 by 2 into again 1 by 2 plus 1, and then it is h upon 2 pi. So what is that? That is here 3 by 2. Okay, I will write it here. 1 by 2 into 3 by 2 into h upon 2 pi. So what it will be? It will be your under root of 3. Then it will be your here 4 under root of 3 by 2, right? It is h upon 2 pi. Got it? So this will be the spin angular momentum if you just take the spin of an electron as plus 1 by 2. So have you noted down this?
Yes, sir.
Okay, then questions are asked that which of the following quantum number is not possible? So can you answer this one question, that which of the following quantum number, which of the following quantum numbers is not possible? So you have to tell which is not possible. This is very important. So for example, if I will give you one of the option is, let's say n value is 1, l value is 0, m value is also 0, s value is, let's say, plus half. So let's see the next one. N is your 4, L is your 2, M is, let's say, minus 1, S is minus 1 by 2. Yeah, plus 1 by 2. Okay, next I'm giving here, that is N value is 0, L is 0, M is also 0, S is plus 1 by 2. Next, I may write it here, that is N value is, let's say, 5, L value is here 4, M value is here minus 2, S value is here plus half. So can you tell me which is not possible among these options? Can you tell me which of the following set of quantum numbers is not possible? I hope you can solve this. See, this actually, you know that the first principal quantum number, what is the value of n? Principal quantum number. That is 1, 2, it can have any value greater than 1. But here, if you can see that n value is given 0, right? So this will be your not possible. So it's not possible. So you have to tell which of the following quantum number is not possible. So that means this is not possible. C option is not possible, right? Have you got it?
Yes, sir.
Shall I move to the next page?
Yes, sir.
Okay. So now tell me, for example, now if question is given to you that, for example, let's say we're having electron is present in, let's say, 3p(z) orbital. So let's say we are having 3pz orbital and there is electron in this, and you have to tell me all the quantum numbers for this one. So can you tell me what will be the first quantum number n value? So here it is given that it is 3p, so that means n value is 3, right? Then L value, for p L value is 1. I hope you remember that box table. I have shown that for S L value is 0, for p L value is 1, and what will be the m value? Now this is your pz. I hope you remember I have told you the sign convention that for pz m value is taken as 0, right? Do you remember that?
Yes.
Exactly. So S value, it can be either plus half or minus half. So this is how to write quantum numbers for any electron which is present in any orbital. For example, okay, let me write that. You have to write, okay, I will write all the 4 quantum numbers, write all the 4 quantum numbers for an electron in 4px orbital. So can you write all the possible ways here? So first of all, tell me what will be the n value, principal quantum number. N
4.
value, it is given here, it is 4 exactly. Okay, what will be the L value? For p, L value is always 1, whether it is px, py, or pz, L value is always 1. And what will be the m value? M
Plus
value
or
can
minus
be
1.
now, exactly, it can be either plus 1 or it can be minus 1, because for pz, m value is 0. And spin can also be either clockwise spin or it can also be anti-clockwise. So you can write plus minus half. So is it now clear? Shall I move ahead? Shall I move to the next page?
So if it was 4s sx, well, then L is 0.
Exactly. For S, L value is 0. Okay, I will write it here that, for example, let's have here, for example, if I'm having an electron in, let's say it is your 5s orbital. So we know that for 5s, so first of all, n value will be here 5. Then the L value, for S, L value is 0. You have to remember this. For S, I hope you remember that table. I have told you that, what I have told you, that for S, L value is taken as 0, L value is 0, and for P, L value is 1. And similarly for D, I told you that L value will be 2. And for similarly F, what will be the L value? 3. Similarly, if there is another orbital, that is G, L value will be 4. So you have to remember this table. This is very important because we use it everywhere. So here you can see that when L value is 0, so now can you tell me what will be the M value? When L is 0, M will be also 0. And what will be the spin? So whenever we have any electron, it can move in the clockwise or anti-clockwise direction. So you can show it plus half or minus half. So this is the correct way. So got it now?
Yes, sir.
Okay, then let's move towards another very important principle that is known as Pauli's exclusion principle. Pauli's exclusion principle. So what is this Pauli's principle? Pauli's exclusion principle, it states that an orbital can accommodate a maximum of 2 electrons with opposite spin. So this is very important. I will write it, its statement like this. So according to Pauli, an orbital can accommodate maximum of 2 electrons with opposite spin. So that means whenever we have any orbital, for example, let me take as S orbital. So S orbital is always spherical, right? Let's say this is your S orbital. So how many electrons it can accommodate according to the Pauli's exclusion principle? It can only accommodate 2 electrons. So the spin of one electron, it will be up. So this is up spin. And another electron, if it is there, it will definitely have down spin. So this is very important. So I hope you remember that this arrow, it represents the up spin. And similarly, this down head arrow, it represents the down spin, right? So that means you have to remember that according to the Pauli's exclusion principle, whenever we have any orbital, it is not only necessary that we're having p orbital, s orbital. It can be p orbital, it can be d orbital, it can be f orbital. Any orbital can accommodate only maximum of 2 electrons, only 2 electrons, maximum of 2 electrons. And there should be opposite spin. So that means one electron, it will just move in the clockwise direction, and another will just move in the anti-clockwise direction, right? So clockwise and anti-clockwise direction. So that means one should have up spin, another electron should have down spin, so that it will be stable. Otherwise, there will be repulsion more and it will be unstable. So that is why, according to Pauli, the 2 electrons which are actually inside an orbital, they should have opposite spin. This is very important. So have you noted down this? Shall I move ahead on the next page?
Yes, sir.
Okay, so now this is one of the statement. You can also define this Pauli's exclusion principle like this. That is, no 2 electrons in an atom, no 2 electrons in an atom can have all the 4 quantum numbers, all the 4 quantum numbers to be same. That means 3 quantum numbers can be same, but the 4th quantum number, it must be different. It should be different. It cannot be same. For example, if I'm just talking of helium, in case of helium, I'm having atomic number 2. So that means it has 2 electrons, right? It has 2 electrons. So that means if, let us say, 1 electron, let's write the quantum numbers for this first one of the electrons. So n value will be, let's say n value is here 1. So what will be the L value? Actually, in case of helium, electron is present in the s orbital. So for s, L value is 0. So m value will be also 0. So what will be the spin? Spin quantum number, it will be, let's say, plus half. One of the electron is having clockwise spin, right? Then tell me, for another electron, what you will write for another electron. That is the second one electron, which is actually there in case of helium. And the quantum numbers will be just like this. That is, n will be the same, that's 1. L will also be 0. M will also be here 0. But S will be now having minus half. S will be having minus half. This will be the difference.
चाबी दे दूं मैं उनको स्वयं के साथ और सामान्य सिगारा अभी
Have you noted down this?
Yes, sir.
Is my voice audible? Have you noted down this?
Yes, sir.
Okay, so what you got here? We have got that in case of 2 electrons in an atom, the 3 quantum numbers can be same. For example, n value is here 1, here it's also 1. L value is 0, here it's also 0. M value is here 0, here it's also 0. But here you can see that spin is plus half, and here the spin is minus half. Spin is here plus half, here it's minus half. So that means the 2 electrons in an atom, they cannot have all the 4 quantum numbers to be same. So no 2 electrons in an atom can have all the 4 quantum numbers to be same. So this is another way to define the Pauli's exclusion principle. I hope that you have got this. Have you got it? Is it clear?
Yes, sir.
Okay, so this was the Pauli's exclusion principle. Then we have to move towards the another topic, that is actually the shapes of orbitals. But before that, now you should be able to tell how many subshells will be there in a particular shell, how many orbitals will be there. I will just give the formulas with the help of which you can tell the number of electrons, the number of subshells, right? All those. Okay, for example, if you had to tell number of subshells in any shell, number of subshells. So number of subshells, it is just given by the formula, that's n, principal quantum number, right? And similarly, if you have to calculate the number of orbitals in a subshell, number of orbitals in a subshell, so that is given by 2l plus 1. Number of orbitals in any subshell, that will be given by 2l plus 1. So you have to remember this formula. So you know the L value. For S, L value is 0. For P, L value is 1, right? So for D, L value is 2. I hope you remember that. And similarly, can you tell me number of electrons? Number of electrons in a subshell. So that is calculated by number of electrons in a subshell. So that is calculated by, that means you will just remember that in a particular orbital, 2 electrons can be accommodated. So that means you will just multiply this 2 with this 2l plus 1, right? 2l plus 1. So that means the formula will become 4l plus 2. Got it? So this is how to calculate number of electrons in a particular subshell. So I am again repeating that the number of subshells in a particular shell, that is given by n value. So for example, if n value is 2, so that means there will be 2 subshells. And the number of orbitals in a subshell, that is given by 2l plus 1. That is given by 2l plus 1. And the number of electrons in a subshell, so that is given by 4l plus 2. So have you noted down these formulas? Shall I move to the next page?
Yes.
Sir.
Okay. So then the next formula which you can remember, that is number of electrons in a shell. So that is given by which formula? Number of electrons in a shell. So that is given by 2n square, right? 2n square. So with this, you can calculate the number of electrons in a shell. And then you can also tell the number of orbitals in a shell. Number of orbitals in a shell. So if you have to directly tell the number of orbitals in a particular shell, you can also calculate this with the help of the formula, that is n square. That's n square, right? So that it will become clear. So tell me that how many electrons can be accommodated in a subshell? So can you tell me how many electrons can be accommodated in S subshell? So just tell me the answer. How many electrons can be accommodated in S subshell? Yes, exactly 2. And how many in the P subshell?
6.
Exactly 6. And in case of D subshell, it will be 10, right? And in case of F subshell, it will be 14. So I hope you have got it. In case of S subshell, maximum electrons that can be accommodated, that is 2 electrons. In case of P subshell, we are actually having, we are having 3 p orbitals, px, py, and pz. Each orbital can accommodate 2 electrons. So therefore, 3 p orbitals, they will accommodate maximum 6 electrons. Got it? In case of D, it will be 10 electrons. And in case of F subshell, it will be 14 electrons. 14 electrons. Is it now clear? Have you got it? Because in case of s subshell, there is actually one s orbital, right? One s orbital. And I told you that an orbital can accommodate maximum 2 electrons. That's why there will be 2 electrons in s subshell. But in case of p subshell, there are 3 p orbitals, right? There are 3 p orbitals. That is px, py, and pz, and each can accommodate 2 electrons. So that means 3 p orbitals will accommodate 6 electrons. And in case of d subshell, there are 5 d orbitals, right? There are 5 d orbitals. So each orbital can accommodate 2 electrons. So 5 orbitals will accommodate 10 electrons. And in case of f subshell, there are 7 f orbitals, right? There are 7 f orbitals. So that means in total, the electrons which can be accommodated, that will be 14. Have you got it? You can also calculate it with the formula, which I have already told you. What was the formula? Formula was, that is 4l plus 2. This is how to calculate number of electrons in any subshell. For example, in case of S subshell, what is the L value? L value is 0. So that is 0 into 4, that is 0. 0 plus 2, that is 2. In case of P subshell, what is the L value? L value is 1. So that is 4 into 1, that is 4. 4 plus 2, that is 6. Got it? In case of D subshell, what is the L value? L value for D is 2. So that means 4 2s are 8. 8 plus 2, that is 10. And in case of F subshell, what is the L value? L value is 3. So that means 4 into 3, that is 12. 12 plus 2, that is 14. So I hope that it is now clear. You can tell me the number of electrons in any subshell. So can you?
Yes.
Okay. So now tell me, if I will just tell you that how many electrons can be accommodated in G subshell. G subshell. For example, let me write it here that I'm having the G subshell. So what is the L value for G? It's 4, right? Therefore, can you tell me how many electrons can be accommodated? It will be now 4l plus 2, right? 4l plus 2. So that is 4 into 4 plus 2. That is 18, right? Got it? Is it now clear?
So,
Okay. Okay, then we have to study the shapes of orbitals. I hope that now you can solve questions on this. Shall I move to the topic, that is the shapes of orbitals, or shall I give few more questions? Can you tell me? Shall I give few more questions, or shall we discuss the shapes of orbitals? Okay, let's solve one more question, then we will move ahead. So calculate the total number of orbitals in M shell. So can you tell me this one? So just calculate and tell me the answer.
Sir, is it 9?
Exactly, the answer will be 9. So which formula you have used it here?
Sir, first I found L, so it will be 0, 1, 2.
Yeah, you can just first tell the
Then I did
subshells
12,
and then you
then
can
I did
calculate the orbitals.
12.
But there is also the direct formula. I have told you the direct formula is n square. Now we know that for k, what is the n value? N value is 1. For similarly, L, what is the n value? N value is 2. And for the M shell, what is the n value? N value is 3, right? So that means you will just write the 3 square. So 3 square means 9. So there will be total 9 orbitals in case of M shell. Got it? So any doubt here? So now can you tell me the number of electrons in O shell? Number of electrons that can be accommodated in O shell.
25.
That can be accommodated in O shell.
Sir, 25.
So what is that? How to calculate this? What is the formula? I have told you the formula. Formula is 2n square, right?
So 50, sir. Sir.
So that is for M, n value is 3. For n value is 4. And for O, what will be the n value? N value will be 5. So that means you will write 2 into 5 square. 5 square, that's 25. 25 into 2, that is 50. So that means 50 electrons can be accommodated in O shell. So have you got it? Is it now clear?
Yes.
Shall I move to the next page? Have
Yes,
you noted
sir.
down there? Okay. So then let's see here the shapes of orbitals. Shapes of orbitals. So first let's see the shape of s orbital. So I have told you that s orbitals have spherical shape, right? I hope you remember that I have told you that s orbitals have spherical shape, right? Spherical shape. So that means if you just write this is the nucleus, let's say these are the electrons which are outside this nucleus. If it is the spherical in nature, so that means the shape is spherical. So s orbitals have spherical shape, right? Let's say this is the shape of s orbital. So let me call it as 1s. So this is the shape of 1s orbital. So can you tell me what will be the shape of 2s? Will it be spherical also? Yes. So you will remember that all s orbitals are spherical. All s orbitals are spherical. So that means whether it is your 1s, whether it is your 2s, whether it is your 3s, so all s orbitals are spherical. But there is difference. One difference is in the size. I have told you that 1s, it has smaller size, right? 2s has bigger size. 3s will be having very big size. Then it will be your 4s. 4s is also having very big size. So just on. So that means in case of 2s, one difference is in the size. But along with that, there is another difference that is very important. The difference is actually there is a space where the probability of finding an electron, that is 0. So that is actually known as node. So you'll write it here. That in case of 2s orbital, and there is a space outside the nucleus where the probability of finding an electron that is 0, so that's called the node. So I will write here, this is the shape of 2s orbital. So now you can clearly see here that there is a space here, this space where there isn't any electron, so that's called the node. So what is node? I'll write it here. What is node? Node is the 3D space where the probability of finding an electron is 0. Where the probability of finding an electron is 0. So that means here you cannot find any electron. So such a space, such a 3D space, it is called a node. Have you got it? So this will be the shape of 2s orbital. So this is just the shape of 2s. So you can see that 2s, it is bigger in size as compared to 1s, and there isn't any node in case of 1s, but there is one node in case of 2s. Now on the basis of this, can you tell me what will be the shape of 3s? The shape of 3s, that will be also spherical, isn't it? But what will be the difference? Difference will be that in case of 3s, there will be 2 nodes, right? In case of 1s, there is no node, there is 0 node, right? In case of 1s, there isn't any node. Okay, I will first write it on the next page. Have you noted down this? Shall I move to the next page?
Yes, sir.
Okay, now first remember that nodes are of 2 types. Nodes are of 2 types. The node which you are actually seeing here in case of s orbital, that is known as radial node. So nodes are of 2 types. Nodes are of 2 types. One type of node is known as radial node. So the node which I have shown here, that is the radial node. This node is also known as spherical node. Radial node, or what we call it as spherical node. Radial node or spherical node. So how to calculate radial nodes? The formula is n minus L minus 1. This is the formula with the help of which you can calculate the number of radial or spherical nodes. For example, if I just talk of 1s, so can you tell me how many radial nodes will be in case of 1s? So what is n value? N value is here 1 minus what is L value? For s, L value is 0, right? And then it is the formula minus 1. So 1 minus 1, that is 0. So there isn't any node in case of 1s. But if we just talk of 2s, so that is 2 minus 0 minus 1. So that's 1. So there is one radial node or spherical node. In case of 3s, what will be the radial nodes? How many? That is 3 minus 0 minus 1. So that's here 2. And in case of 4s, there will be total 3 spherical nodes. So have you got the difference between 1s, 2s, 3s, 4s? All will have spherical shape. The difference lies here in the size. 1s will have smaller size, then the 2s, it will have bigger size, then 3s, then 4s. Also, in case of 1s, there isn't any node, there isn't any radial node or spherical node. But in case of 2s, there is one spherical node, and in case of 3s, there are 2 spherical nodes, and in case of 4s, there will be 3 spherical nodes. Got it? Have you got it?
Yes, sir.
Okay. So then we are also having another type of node. So that is known as angular node. That is known as angular node. Angular node, or it's also known as nodal plane. It's also known as nodal plane. And how to calculate this? This is simply calculated by the formula, that is L. It is given by the formula L. So whatever the value of L, so that will be the number of angular nodes, or what we called as nodal planes. So we know that in case of whether it is your 1s, whether it is your 2s, whether it is your 3s, or any s orbital you are having, for all these s orbitals, we know that L value is 0, right? For S, L value is 0. So therefore, you will remember that in case of s orbital, there isn't any angular node. So you'll write it here that in case of s orbital, in case of s orbital, there is not any nodal plan, or what we can also call it as there is not any angular node. Got it? So have you got it? You can also see it diagrammatically, for example, graphically. For example, if I just plot a graph, let me show it here. For example, if I just plot a graph between the psi square is the, I hope you remember, it is psi is the wave function, and psi square, I told you that it represents the probability of finding an electron. It gives the probability density. So if I just plot the graph between psi square versus r, the radius, what we see in case of 1s, graph is just like this. So that means there isn't any node. Okay, let me show it like this. Graph will be just like this. So that means with the distance, what happens? Let's say this is here the nucleus. This is the nucleus. So near the nucleus, electron density is very high. Then when we just move away from the nucleus, the electron density decreases. This is the graph for 1s. This is the graph for 1s. But now if I'm having 2s, what will be the graph? So in case of, let me show it here. Let's say this is the graph I'm plotting between the psi square versus r. So first of all, electron density is very high around the nucleus. That means near the nucleus, then it decreases. Then there is such a space where there isn't any electron. That's called the node. And then it again increases, then it decreases. So this is here the node. You have to remember this. So this actually here represents the node. So that is the radial node. So in case of 1s, there isn't any node, but in case of 2s, this is the graph for 2s. So that means in case of 2s, there is one node. You can see it. There's one node. So have you got it? These two graphs are very important. They are actually given on your textbook. So have you noted down this?
Yes, sir.
So shall I move to the next page?
Yes, sir.
Okay. Then let's see the shapes of p orbitals. Let me show here the shape of p orbital. So tell me what is the shape of p orbitals? So p orbital has dumbbell shape. They have dumbbell shape. Dumbbell shape. Dumbbell shape means that there are actually two lobes. I will just represent like this, that this is the nucleus, and electrons will be just in these two lobes here. So this shape is known as dumbbell shape. This shape is known as dumbbell shape. Got it? This shape is known as dumbbell shape. So that means they are just simply two lobes. One is this lobe, electrons are inside this, and there's another lobe, electrons are in this. So let's say this is your 2p, and let's say this is your 2px, right? What will be the shape of 2py? Let's say this is here your x-axis, right? Let's say this is here your x-axis. So if I just draw here, let's say this is your y-axis. So that means if you just draw, this is, let's say, the nucleus. That means the electron cloud, it will be just like this. Correct? Are you getting this? So this shape is known as a dumbbell shape. So whether you are having 2px, whether you are having 2py, or whether you are having the 2pz, all these will have the dumbbell shape. Got it? These will be the shapes of p orbitals. So p orbitals have dumbbell shape. That means there are two lobes in which these electrons are present. So this is your 2pz. 2pz. Correct? So can you tell me, is there any radial node in this 2px? So number of radial nodes. How to calculate number of radial nodes? I have given you the formula. So can you tell me number of radial nodes? So that's given by n minus l minus 1, right? So what is n value? N is here 2. What is l value? For p, l value is 1 minus 1. So 2 minus 1, that is 1. 1 minus 1, that is 0. So there isn't any radial node in case of, there isn't any radial node in case of 2px. Got it? So can you tell me, is there any radial node in case of 2py, 2pz? No, because when 2px is not having any radial node or the spherical node, so there will not be any radial or spherical node in case of 2py, and similarly in case of 2pz. Now, can you tell me the number of angular nodes here? Number of angular nodes. I hope you remember the formula. What was the formula of angular nodes? That's actually given by the formula L, right? So what is the L value for P? For P, L value is 1. So that means they have one angular node. That is also called the nodal plan. I hope you remember that is also called the nodal plan, correct? So where is that? That is actually here. You can see this. Can you tell me, is there any electron lying in this plan, which I have shown by this red? This is the plan here. So is there any electron in this plan? So this is called the nodal plan, or what we also call it as, angular node. Got it? So in case of 2py, you can also see here that this is your the nodal plan. And similarly, in case of 2pz, here you can see this is your nodal plan. Got it?
Yes, sir.
Is it clear? Exactly. So in case of p orbitals, they are having one nodal plan or angular node, and in case of 2p, there isn't any radial node. But if I just talk of 3p, will there be any radial node in case of 3p? Can you tell me? Okay, let me draw the structure of 3p on the next page. So let's say, for example, this is the nucleus. Then first electrons will be just like this. This is dumbbell shape. Then what will be next? Next will be that there will be node. And after that, there will be electrons. You can just draw this structure on your notebook. So what is the difference between 2p and 3p? This is the shape of 3p. This is the shape of 3p. Let's say this is the 3px. So I hope you can clearly see here that there is some node here, that is a radial node, right? Or you can also call it as spherical node, radial node or spherical node. So we know that the radial node, it is given by n minus l minus 1. So that is here, n is your 3 minus, for p, l value is 1 minus 1. 3 minus 1, that is 2. 2 minus 1, that is 1. So therefore, there is one radial node. And now can you tell me the nodal plan here? How many nodal plans will be there? Nodal plan, it is given by the formula L. So L value is 1 for any p orbital. So therefore, it has one nodal plan. Got it? Now, if question is asked that how many total number of orbital, total number of nodes are there? Can you tell me the total number of nodes? In case of 3p, how many are there, the total number of nodes? Total number of nodes is given by the formula, that's n minus 1. Will you remember this? N minus 1. So that means n value is here. What is the n value? N value is here 3. So 3 minus 1, that is 2. So total nodes are 2. And among these two, one is your radial node and another is your angular node, or what we also call it as nodal plan. So have you noted down this? It's very important.
Yes, sir.
So is it clear?
Yes, sir.
So let's then revise what we have discussed today. So today we studied just from the quantum numbers. I told that these quantum numbers, they are just the set of 4 numbers, which gives the complete information regarding the electron. And that means their energy, we can tell the size, the shape of the orbital, the orientation of the electron, the spin of the electron. Each and every information, it is given by the 4 quantum numbers. So the first quantum number is known as principal quantum number, that is represented by small n, and it gives the information about shells. You can also say the size of the orbital. Next, I told that is the azimuthal quantum number, that is represented by small l, and that gives the information about subshells, right? And then I told that L value is calculated by the formula that is 0 to n minus 1. And the next I told you that that is the azimuthal quantum number. With the help of this azimuthal quantum number, we can also calculate the angular momentum of an electron. So that is given by the formula square root of L into L plus 1 into H upon 2 pi. Next, I told you the magnetic quantum number, that is represented by m, and it gives the information about orbitals. And how to calculate the m value? That is simply calculated by the formula minus L through 0 to plus L. So we have seen that in case of S subshell, there is only one S orbital. In case of P subshell, there are 3 P orbitals. In case of D subshell, there are 5 orbitals. And in case of F subshell, there are 7 F orbitals. Got it? Then we have discussed about the fourth quantum number, that is the spin quantum number, that gives the information about spin of an electron. Spin means when electron rotates on its own axis, that's called the spin. So spin can be either clockwise or it can be anti-clockwise. That means it has only 2 values, plus half, minus half. We also call it as up spin or down spin, right? Then after these quantum numbers, we had discussed the shapes of orbitals. We first told you that S orbitals has spherical shape, P orbital has dumbbell shape. There are 2 lobes. And then I told you that how to differentiate different orbitals. There is actually node. There are 2 types of nodes. One is known as radial or spherical node. Another is known as nodal plan or angular node. And how to give the number of radial nodes? It is given by the formula, that's n minus L minus 1. And angular nodes is given by the formula, that is L, small l, that is the azimuthal quantum number. And then you can calculate the total number of nodes. Total number of nodes is given by the formula, that is n minus 1. So I hope that you have got it. If there is any question, any query, you can tell me. Then we will conclude today's class. So are you having any doubt?
No, sir.
Anybody? Okay, then let's stop today's. I think, yeah, time has gone, right? Yeah, so let's stop today's class here. Have a nice day ahead.
Thank you, sir.
Most welcome.
Thank you, sir.
Most welcome.